Great. So 2.4 notes, distribution shapes. We'll start by talking about some broader categories of the distribution shapes after we define what a distribution shape is, and then we'll talk about some more specifics, and then we'll look at an example. So starting with the definition of distribution shapes, that's key. What is a distribution shape? A distribution shape is a graph, table, or formula. Graph, table, or formula that provides the values of the observations and how often they occur. The shape of a distribution often plays a role in the appropriate method for statistical analysis. More to come in later chapters. To identify the shape of a distribution, use a smooth curve that approximates the overall shape. Most often, we'll be using a histogram related to a relative frequency distribution or a frequency distribution to talk about distribution shapes. So that's what's in this picture here. You can see how the curve overlays the histogram, and that's actually a bell-shaped curve, and that's the one we will access most often when applying our statistical analysis methods in chapters to come. So our three broad categories for shape are modality, symmetry, and skewness. Starting with modality. So observe the peaks or the highest points. Think of mode. That should be a word that we recognize. Mode is how often the data occurs, or the number that occurs the most often. So you can see a peak would be, if we put little bars underneath it for a histogram, that would be the highest bar, which relates to the value that occurs the most often. So unimodal is one peak. That's this first picture here. Unimodal. Bimodal is the one with two peaks. Bimodal. And multimodal, three or more peaks. Yes.
All of the peaks have to reach the same point?
Good question. You can just tell that they're kind of higher than most of the other data. So relatively the same height. Doesn't have to be exact. Symmetry. So we all know that word as well. Symmetry. Now applied to our histograms and distribution shapes. A distribution that can be divided into two pieces that are mirror images of one another is called? Symmetric. Symmetric, mirror images. Think of a butterfly. Symmetry. Notice, so we've got these three examples of symmetric distribution shapes below: bell-shaped, triangular, and uniform or rectangular. The bell-shaped and the triangular are not only symmetric, they could be called? Yes. Who said unimodal? Nice. So they have a peak, one peak. Skewness. Got some great pictures here. Forgot to edit my text. I had to cross that out. Come back to that thought. We have skewed. What comes to mind when you think of the word skewed?
A little pointy thing that you put in.
A skewer? Okay. Anything else besides a skewer or a kebab? It's a common first answer. Skewed. You don't use that? You never use that? It's okay. Yes? Okay, stuff leaning. Leaning Tower of Pisa. Italy. Great. Thanks. Multicultural today. Appreciate it. So yes, we're talking about skewed, and in this case, we're talking about data where you have most of the data collected in one area, but then there's some data that kind of pulls the shape of that graph, skews the shape of that graph in one direction or the other. So when you have those kind of outlier data, it might pull the graph shape to the left, in which case we call it left skewed, or might have most of the data here in a central location and then some outliers, or just a smaller amount of the data off to the right, which would be a right tail or right skewed. So the words that we're going to write along with this would be a unimodal, so it is a unimodal distribution. That is not symmetric. It is right skewed or left skewed. I like the picture of the whale with the tail because that helps me remember these pictures where the tail is kind of the skew part of the data. Remember, the higher bars in the histogram are the ones where the data occurs most often. So the highest one is would be the mode of the data set. Make sure everybody's got that. General versus specific classifications. I've already referenced this. General shape classifications would be modalities, symmetry, skewness. More specific would be those subcategories like bell-shaped, left-skewed, triangular. Here's an example. We'll give the specific classification here. Household size. The relative frequency histogram for household size in the United States is shown in this figure 212A based on data contained in the current population reports, a publication of the U.S. Census Bureau. So much data you can find about the U.S. If you just look up the Census Bureau's website, find cool information like this. Distribution shape for sizes of U.S. households is, so here's the basic histogram that you would see. You can see that a curve has been drawn over top. Which one of the distribution shapes specifically, specific classifications do we see there? Right skewed. Yep, simple as that. Tails off to the right. Notice 7 people per household is not a common occurrence, whereas 2 people per household is the most common occurrence. So right skewed is how we would classify that distribution shape. Last section, population and sample data versus distributions. This is maybe going to blow your mind a little bit. Maybe make your mind just feel like you're seeing the same words in different ways, and it all starts to feel jumbled. But we will look at an example, and these things will play out in further in lessons to come. So feel free, it's okay to kind of not have 100% clarity on this topic by the end of today, but like I said, more clarity will come even in chapter 3 as we get into to this topic on a deeper level. It'll make more sense. So you just kind of have to trust me on that. So we'll talk about population and sample data. Those are the values of a variable for the entire population. So we're talking about the values of a variable for the entire population. What else do we call when we have the values of the variable for the entire population? What else is that called? I heard it. Not a sample. Census, yes. So we sometimes, occasionally, have all of that information. A census is one of the few times we have access to the full data set. Sample data is the values of a variable for a sample of the population, good. Population distribution, AKA distribution of a variable. So note that these are synonymous, population distribution and distribution of a variable. And that would be the distribution of the population data. Right, so when we create that histogram and we have all of the population data, then it's called a population distribution or a distribution of the variable. Sample distribution, last blank, the distribution of sample, good, sample data. Does anyone feel that head spinning feeling of all of those words we're just using a lot of different ways? Maybe you feel full clarity right now. That's good, okay. Maybe I'm all by myself in that. That's good. Example. So here's this example we're coming back to. We just referenced the household size. So we considered the distribution of household size for U.S. households. Here, the variable is household size, and the population consists of all U.S. households. And then we repeat the graph. So that's repeated, the same graph as on the previous page. The graph is a relative frequency histogram of household size for the population of U.S. households. It gives the population distribution or the distribution of the variable, same thing, for household size. We simulated 6 simple random samples of 100 households, each from the population of all U.S. households. So each one of these orange graphs represents a sample distribution. So figure 2.13b shows relative frequency histograms of household size for all 6 samples. Compare the 6 sample distributions to each other and to the population distribution. So pause for a moment, look at each of these orange graphs, compare them to one another, and compare them to the population distribution. What do you notice is similar? What do you notice is different? I'll let you think about that quietly for a minute. All right, raise your hand if you can tell me something that you've noticed, something, a similarity or a difference. Sydney? They're all right skewed. Good observation. So just like we said previously, so about the population distribution, they are all right skewed. Max? 2 is always the peak, the mode, good. Kylie?
Sometimes, like, on quite a few of these, there's, no data on 7. It's complete, like, it's at 0.
Okay. Good observation. So not in 7 does not occur in every sample distribution. 7 people per household. William, I saw your hand. Did it already get 2? Okay, 2's the mode. Anything else? Similarities, differences? Jacob?
In most of these, the distribution follows 4 follows 3. So 3 has a higher relative frequency than 4, apart from just one of these, in which 4 has a higher frequency than 3.
Okay, good observation. So like in that bottom left, they kind of switch places there. Anything else? Good observation. In conclusion here, we look at these different sampling distributions. None of them is exactly the same as the next one. And none of them exactly matches the population. That'd be a big fluke if that happened. It's possible, not likely. So a key statement is in this blue box below, population and sample distributions. For a simple random sample and sample distribution approximations, the population distribution, i.e., the distribution of the variable under consideration, The larger the sample size, the better the approximation tends to be. So that's the key statement. Larger sample size, you're going to get a sampling distribution closer to the one that is the actual population. Make sense?
Makes sense?
Great. That's 2.3. 2.4, like I said, sampling distributions.